on this computer. Cool. Okay, it's working. Okay. For anyone who was here prior to the recording, I wrote in stuff here. It's gone now. If you want to know about it, email me and I'll tell you. Okay, so part C. Is the salt form of codeine more or less soluble than the free base form of the drug, and why? So for this, more soluble. The rationale, salts dissociate. That's spelled relatively correctly. But when you put salt into water, for example, NaCl, which are ionically bonded, we end up getting a Na plus with water between it and Cl minus. So by putting that phosphate, codeine phosphate into water, that codeine and that phosphate are going to separate, and the likelihood that the positive and negatives participate in the hydrogen bonding is going to increase, which increases its solubility overall. Good? Okay, we'll say it's good. If you have questions, let me know and we can touch back on it, but salts dissociate in water. Last but not least, what is the chemical consequence of mixing aqueous solutions of each drug in the same IV bag? So the short answer is precipitation can occur. Now, this is the short answer because it is very much a simplification. The thing that would normally govern this in chemistry is solubility tables. Which is X group with Y metal equals soluble or insoluble. Well, when we're dealing with drugs, we don't have tables like this that you can kind of run through. I mean, like Trissol's IV compounding that was used in lab in the second semester does do a lot of this based on studies that have been done. But for how does it apply to this handout specifically, we've got Pen V, codeine phosphate. Up here we've got potassium, and down here we've got, sorry, let me erase that. We've got codeine to phosphate. This is positive, this is minus, this is positive, this is minus. If we put these into water, there is potential that C plus will connect with Pen V phosphate. Now there is, I didn't count them, many carbons over here, and over here we've got many carbons as compared to like small molecules. Which if we think about the molecular weight issues of 500 molecular weight being ideal for small molecules, if these two were to come into contact with each other and bond, their weight would probably go above this 500. and the chance of precipitation occurring is a lot higher. Which is why things either have to be put in separate bags or they have to be separated by time to make sure there's no interaction. But that is the rationale behind the mixing of these solutions, is that will it definitely occur? No. But statistically speaking, the chance of these things interacting, connecting, and then leaving the solution because they get so heavy that the water can no longer keep them dissolved is a possibility that they've run into in hospitals. Does that make sense? Awesome. I am ready to move on from this handout. Does anybody have any questions before we move on? You can say no, or you can type it in the chat.
I actually have a question.
Sure thing.
When we took exam 1, she had provided us with a question that there was 3 drugs, and then she asked something within the lines of, will they interact? Are they bad? Something like that. I don't remember exactly what the question asked. But if we can do like something similar to like medication, like an
Okay.
example with
Was that like the
3 drugs.
truck driver problem? Like which would be preferred for like non-drowsiness and like absorption? Or was it something different?
No, it was different.
Okay. We can, I don't have anything prepared. With stuff like that, what I would look out for is the chance of positive molecules combining with negative molecules and pulling it out of the solution. Because was the question asked in a way that, like, similar to like, are there consequences, like part D here? And then were you given the structure?
No, I think she had the 3 structures for each drug, and then she had percentage, and then she asked.
Oh, I know what you're talking about. It was, I'm lacking the word, but one of them is an example of, it's plasma protein binding. That's what it is.
Yes, it had
Okay.
to do with that. Yeah.
Yep. So save this. I'm going to leave share and I am going to pull up a whiteboard. Okay. So plasma protein binding. I don't have any structures prepared, so I'm just going to call them like drug X, Y, and Z. That's a horrible Z. Okay. The major player in plasma protein binding is serum albumin. That's the one we really care about. And I think Dr. Ward might talk about the other ones, but conceptually, you can base it off of albumin, and then if you're dealt something different, just apply the concepts correctly. But let's say that you put in 200 milligrams of drug X, and the safe range is a plasma concentration of 50. And this has plasma protein binding of 75%. And then for drug Y, let's say it's also, well, let's go 50 milligrams. Safe is, let's say the whole amount is safe to be in your blood, and it binds at a rate of 80%. So adding these two drugs together isn't going to make it dangerous for you because you're allowed to have 50 milligrams in the blood plasma. With this one, you're allowed to have 50 milligrams in, but it's only going to bind. The plasma will bind it at a rate of 75%. And so that means there'll be like 50 milligrams that are free because 150 milligrams will be bound. Good on that so far? This is a very generic way of explaining it, but then we introduce Z. Z, I think, would be an example of, I want to say warfarin has a absolutely massive plasma protein binding, like 97%. And let's say that a safe dose, I have no idea. I'm just putting numbers in here. Let's say drug Z, not warfarin, but drug Z is safe at 100 milligram. You're dosed at 100 milligrams. It's safe at 5 milligrams. Now, if you put these, or if you take these drugs together, the 97% here is essentially going to, let me draw a red blood cell. We've got 75% of drug X on the surface. If we bring in drug Z, it is going to kick all of this off of the cells. It's going to unbind it from the albumin and take its place because that has a higher binding affinity. Where this becomes problematic is now we've got all 200 milligrams of drug X in the blood, which is 4 times the range that is safe. Does that kind of make sense as to what you were asking? It's when you introduce something with a higher binding affinity, whatever was bound is going to be removed. And it's not like it just leaves your body immediately. It's going to enter your cardiovascular system, which if it's got a safe dosing range and it's removed from the plasma protein, it could quickly climb above the safe dosage range into a toxic range. Does that answer your question?
So the safer one has the less percentage, right? The smaller percentage.
I wouldn't think in terms of safer. I'm saying, for example, so in like kinetics, when we've got the threshold, let's say it's like, for this, I set it at 50. So let's put 50 in the middle. And then above it, we've got 60. I've got a stylus. Why am I doing this? 60 and 40. So we want to be somewhere between here. But if we introduce something with a lot higher binding affinity, this number is going to jump up because it's going to be free in the plasma, which when we dosed it originally, wasn't an issue. But when we added something else, it freed up a lot of drug into the blood, which increased it into the toxic range. Is that better?
Yeah. Okay.
Okay. I'm saying safe as in what we want it dosed at in the blood.
Mhm.
But if you think about a lot of drugs, we will give like really high doses because the amount that is absorbed is a lot lower. So sometimes you have to go a lot above because so much of it is bound to plasma protein. But if you follow it with a drug that has a higher plasma protein binding and kicks it off, well, then that's going to change what your dosing is going to be safe for patients. Good concept wise?
Yeah, it makes sense now. Thank you.
Okay, not a problem. All right. Next up, I want to do log P. And I created one based slightly off of one that was done in SLA. No. Okay, give me 1 second to find it. Here we are. Close that. Can I paste it to a blank sheet? Nope, not that one. Sorry. I cannot. Okay. We rolling with it. This is the structure I created. Almost all of it is the same as one from SLA. The difference is I put a furan ring here on the left because I thought it might be worthwhile to include since we've seen it before on exams. And it's a little different as to how we think about it. So if you guys want to take a second to jot this down, that will work for me. This is a log P problem. Additionally, while you guys were jotting it down, so I know Dr. Ward originally had that handwritten like log P table. Did you guys prefer that or the one that was printed nice and neat for the exams? No opinions? That's fine too. Does anyone need any more time to jot this down? Or do they have the structure down?
It's just white. There's nothing on it.
Oh, you guys can't see this. My apologies.
Yeah.
I learned something about Zoom today. Stop share. Share this. Okay, now can you see it?
Yes.
Okay. If something seems off, let me know. I was under the assumption that you saw what I saw. My bad. I will also give you my opinion on how to best solve log P problems. Because depending on the structure you are given, my opinion changes, and I'll show you what I mean. But I'll let you guys copy this down first. Okay, if nobody needs any more time, I'm going to get started on this. So annotate. Let's pick red because red stands out pretty well. Grand. So if you were to be given a log P problem with like a phenol with a long carbon tail with stuff coming off of it, I would do what Matt and Logan said and start at one end and go to the other. But if you're given something like what I prepared for you guys, I would not do it that way. What I would do is I would look for areas where there's clear groupings. And do each grouping separately. So A, B, C, D. And then you've got your alkanes left over, because you have a lot less alkanes left over if you break it into different spheres. That's my opinion. You can completely ignore that if you don't like it, but I think that this structure is not as linear as some of the ones that are designed to be solved linearly are. Personal opinion. And then for how I go about solving this is, if you guys have the printed log P table up, I'm not sure. Let me do a quick mouse. Close. I don't know if you guys have this table available, but do you guys still see the structure? No, you guys see the table now. You guys see the table, yes?
Yes.
Okay, just making sure. I essentially will go down the table and just check stuff off as I see it. That is also a point of like personal preference, but go with it how you feel. So on this, the first thing that jumped out to me is we have 3 phenyl rings. Draw 1, 2, 3. This is going to account for a lot of our lipophilicity. So here I will put phenyl. Phenyl by their nature are aromatic. And then I will put 3x to imply we have 3 of them. And then I put their value as an individual, which is 1.96. And then that equates to 5.88 overall. Did everyone see how I did that?
Yes.
Yeah.
Okay. That's like the only one where there's a lot of them. So good on that. Next up, if you go down the table, the next thing you're going to arrive at is a primary amine. So, which is this guy here. So we're getting rid of this one right now. We can cross it out. It is on a phenyl ring. So I will put an AR to the left and a little squiggly to show I'm denoting the primary amine. We've got one of them. And the primary amine is negative 1.23. Now, I don't know if you guys prefer to draw tables or what, but I think it's important to not make a mistake of putting a misleading minus in front or potentially mistaking it as just a spacer. So when I draw my negative log P ones, I actually put them in parentheses because that is something that they do in like accounting and finance. So 1.23 in parentheses means I'm going to be subtracting it. Next up, we've got an aromatic tertiary amine right here, times 1. And so that is going to be 0.18, which is 0.18. Following our tertiary amine, we've got an aromatic alcohol. So this is down here. AR alcohol. Only one of them. What that accounts for is negative 0.67, which is 0.67 in parentheses. Next up on the list, and I made the mistake, I did skip alkene and ether. Ether's toward the bottom, but alkene is like, I think, second. So I do the furane later just because I want to draw special attention to it as to how we take it apart. So next up is going to be our methoxy, which is aromatic. This guy here, let's get him crossed off. Methoxy, 1x. This is minus 0.02, which equates to, in parentheses, 0.02. We've got our aromatic C acid. That's also aromatic. Our aromatic C acid, which is up here, cross that out. And that rings in at negative 0.32. So, okay. Now, the way we break down alkenes, I mean, not alkenes, furane ring is, furane by their nature are aromatic, but we don't have a group for furane. So what we have here is an aromatic ether and 2 aromatic alkenes. And remember, alkenes are counted by the individual carbons. So first up, aromatic ether times 1. That is simply negative 1. So 1.00 subtract. And then we've got aromatic alkene 4 times, because we've got 4 carbons. And so as an individual, it's 0.82. So altogether, we're going to have 3.28, if my math is correct, which I think it is. And then last but not least are alkanes. So we've got 2 alkanes here in the middle. This is why I like to break up nonlinear groups into separate pieces, because the alkanes at the end are pretty easy. If you've got something linear, do it from one end to the other, but this, it's alkane 2x, it's half per, so 1 overall. And if you add these up, what I got was 7.10, which I would say is lipid soluble. I did not identify any hydrogen bonding. Is there any questions as to how I did this?
I don't have any questions for Lock P, but can you do estimation while we're at a structure?
Sure thing. Let me pull up the table quick because I don't have estimation prepared. We'll just leave that there. Table. No. Okay. We'll do this from I don't have this printed out. I'm going to try and side by side it. Do you guys have a copy of this table or no?
Yeah.
Okay. Then actually, let me grab my other laptop quick, because that will probably yield better results rather than trying to remember what the structure looks like from memory. So give me a second to open my laptop. It should take a minute or less. The reason why I asked if you guys like this table is because I made it for Dr. Ward because I really disliked the old one. And but if people liked the old one better, I can be like, hey, they prefer the old one. Go back. Go. Let me save this drawing. I will send out the pictures afterwards, but I'm going to clear my drawing so we can see. But I did take a picture of that. Okay. So up first, we talked about whether we're going to be using monofunctional or polyfunctional column for estimation method. And 99 times out of 100, it's going to be the polyfunctional because we've got extended groups. So going down our list, the first thing on the list is alcohol. We've got one polyfunctional. It's going to be 3 to 4 carbons. So we always take the lower amount, 3C. Next up, we've got phenol. We have 3 phenol groups. As the polyfunctional, it's 3 to 4. So we are going to see at the most 9 carbon because we take the lower carbon amount. We have 1 ether. Which is equivalent to 2 Cs. We don't have any aldehydes or ketones. I stand corrected on the ether. We don't have methoxys for estimation method. So we actually have 2 ethers. We got there and there. No noteworthy ketones. Amine. We've got 2 amines, one tertiary, one primary. They rank the same according to estimation method. So the lesser is, oh, this only has 1, so 6 carbons for 2. We've got 1 C acid. Which is equivalent to 3 carbons. No esters. No urea, no carbonate, no carbamate. Okay, so what do we have accounted for? Let me get red out. Those are all counted for. Those are all counted for. Those are accounted for. Those are accounted for. Those are accounted for. That is accounted for. That's accounted for. Now, looking at our remaining carbons, we've got 1, 2, 3, 4, 5, 6, 7. So straight up carbons, 7C. Things that are included with this. So let's do kind of how we divvy it up. Our regular C's are 7. And then anything that is part of like the phenol rings are included. So we've got 9 here. So overall, we've got 16. Now, for all the things that are going to decrease it, that's going to be, sorry. I saw the note in the group that they just lost power. I am recording this and I will upload this. So they will have that as an option later. Everything else we're going to include on the other side. So let me switch colors quick. We've got our 3, our 4, our 6, and our 3. So this is going to be 16. Wow. These are actually equal to each other. I think that this is going to be soluble because I think that the ideal difference between them is having 5 more C's than like non-C reducing groups. And because they're equal, this should fall in the soluble category. Does that seem like I did it right? I did not practice for this one, but it's kind of how I remember doing it. Aaliyah?
I'm just looking over it one again. Wouldn't each aromatic, each phenol be 6? So it'd be like 6.
Thank you. You are absolutely right. I don't know why I put 3. Sorry, 1 second.
Oh, that's okay.
I know where I made a mistake. So we don't have an alcohol because phenol is a aromatic alcohol. So doing a quick recount, let's just clear this quick because this is not very good. 6, 6, 6, 1 here, 2 here, there and there. So we've got 18 plus 1, 2, 3, 4, 5, 6, 7. We're looking at 25. We've got switch colors. That's my bad. I don't enjoy estimation method because I don't think it works well, in my opinion. And she really likes to test the more specific, but that's just my opinion. So 2 polyfunctional ethers, that's going to be 4 ether. 1 phenol is going to be 3. Crossed off, crossed off, crossed off. 2 amines, that's going to be 6. Crossed off, crossed off. And then 1 C acid, 3 C acid. Okay, now we have our number. It's 13 to 25. Does that look better? That was my bad.
So the phenol now is only 3 instead of 9.
Correct. So when I read it, I was leaning into phenyl, not phenol. The all implies alcohol, which means we've only have 1. And the phenols I forgot counted as 6 carbons, because that is not part of the chart. That's something that you're required to remember. So non-phenol carbons are 1, phenol carbons are 6, unless they are attached to nothing else. So that would be a phenol with only 1 attachment, and it would be monofunctional, so it would count as 4. But these are not very common. Does that make sense? That's my bad. I was looking only at the chart. I read phenol and I thought phenol. That is all on me. This is the correct way. Any questions with this before we move on?
So it's soluble, right?
It should be insoluble because we have a lot. Okay. Soluble in what?
I mean, when you're comparing it to the estimation of the first numbers you got, if I don't know, I don't remember how we compared it. Because I know
Yep.
like the first one, if it's greater. Go ahead, I'm sorry.
Oh, no, you're fine. The reason why I said soluble in what is technically something will always be soluble. It's just what you are comparing it to. What I want to draw attention to is if we wanted to cross membranes, do we want it to be polar? The answer is no. The 13 here represents its polar solubility. The 25 here on the right is our like number of carbons. Carbons are very lipophilic. So this represents our fat solubility. So it will be fat soluble, but it will not be water soluble. Does that make sense?
Yeah.
Okay. So if you're asked, will this molecule be soluble? I would put either this molecule will be fat soluble or this molecule will be water insoluble. Because you need to state the reference by which you're comparing it. If you're given the just soluble, say which one it is. Say fat or say water, and then say yes or no. Because we have a ton of carbons, that means it is not going to dissolve in water, but it will cross membranes. So it is fat soluble. It is not water soluble. That's something that Balsam drew a lot of attention to. If you ever met with Balsam for tutoring, was that if it says, is this fat soluble? Yes. If is this fat insoluble? No. But if it says, is this soluble? Pick either water or pick like lipophilic fat soluble and then say yes or no if you're given the open-ended prompt, because it is going to be soluble in something. And that difference you need is this has to be 5 or more greater. So if this had been 14 to 13, then it would be water soluble because there's not a difference of 5 between them. Does that make sense?
Yes.
Okay. Are we good on this before we move on?
Yes. Can you also do an example for rule of 9?
Yes. Save that. Clear that. Mouse. Let me go find, I think I've got a document for rule of 9s. Maybe. 3. Nope. Okay, nope. we're gonna just go to a regular whiteboard. Now, with rule of nines, and this is, it's useful in a lot of things. Where we see where we're going to see this most is exam 1. We don't use it much with exam 2 because we can get more into the math of acid base, but this is based around like general acid base principles. So for example, in let's say we've got a pH of 9 and a pKa of 8. So 9 minus 8 equals 1. So the difference we're seeing is to the degree of 1. If we were to have numbers that would subtract to a difference of 2, that would push us, sorry, this is indicative of 1, 9. If we had something that was to the difference of 2, so let's say a pH of 5 and a pKa of 3, the difference is 2, which implies there's going to be 2 9s. And 9s are always put right next to each other. So if you're looking at a ionized versus unionized state, if you've got a number with 1 9, it's going to be 90 and the other one's going to be 10. If you've got a number with 2 9s, it's going to be 99, the other one's going to be 1. And as we go up, we get more and more to a certain state. These will always add to 100 because these are percentages, so they'll add to a 1 whole number. But this would be like a 4th level rule of 9 product. Something that where we did see something like this on exam 2, but we couldn't use rule of 9s for it was ionization state of like that 1 amino acid. And that was in the fall exam where it ended up being like 99.999 rounded to 100% ionized, but she wanted to use math for that. So unfortunately, couldn't apply it as such. But the way that we line this up is for the last piece of information we need is we need a pH, a pKa, and we need to know if it's a basic or acidic molecule. So if it is
Patrick,
acidic,
I have a question. I'm sorry.
oh, you're fine. What's your
Um,
question?
so I know you moved on into ionization, but if she were to give us a pH and pKa, all I have to do was just subtract 9 minus 8 and get a 1, so it'd be like, it'd be 90 and 10%.
Yes. The last part, however, is needing to know whether it's basic or acidic. And
Okay.
that will, it kind of works with Henderson-Hasselbalch. So let's say we're dealing with a basic molecule. The way you're going to set that up is it's going to have our base plus our hydrogen is going to yield the combination of the two, which is that number. So in a state like this, if we add a hydrogen to a base, this becomes our ion. And that means we've got a 1 or a 10% is going to be our ion, which means 90 is going to be unionized. Because the part there is going to be what's the ion. If we were to reverse this example for, let's say, a acid base, I'm sorry, I'm looking at I'm sorry, no, you apply this across the board. So whatever we've got here at, no, I stand corrected. I had it right the first time. With a basic molecule, the 9 is going to represent okay, there's the problem. I was incorrect. There are 4 parts to this. So you need a pH and a pKa. Those are just facts. You don't really interpret those. They're just given to you. You need to know whether it's basic or acidic. And then you need to know the relationship between pH and pKa. So if pH is greater than pKa, you're going to see a greater percentage of unionized. So if pH is greater than pKa, more unionized. However, if your pKa, and this is specific to a basic molecule, if you have a basic molecule where the pH is less than the pKa, you're going to have more ionized. This is applied exactly as the reverse with acidic molecules. So if you have an acidic molecule where the pH is greater than the pKa, you're going to see mostly ionized. And if you've got an acidic molecule where the pH is less than the pKa, you're going to have mostly unionized. So those are kind of the 4 things. Concept-wise, you need to know acid base for the structure, and these 4 rules, these 2 things should be given to you. So for this first one, we were told it's a basic molecule. Our pH is bigger than our pKa. So this top one here, that means we're going to have 90% unionized and 10% ionized. And you apply it throughout. I'm sorry that took me so long to explain. Does that make sense?
Yeah.
Okay. So you need to know if it's acidic or basic, and then you need to remember bases. If it's pH above, it's more unionized. If it's pH below, it's more ionized. And then for acidic, it's the opposite. So if you can remember the rules for one, you can just reverse them for the other. Good on that?
Yes.
Okay. Next up, So we've got log P and the handout done. We also covered some extra stuff. Let's do a protein sequencing next, and then I will circle back to metabolism, because metabolism's a little odd, not odd bad, but odd as in just odd. The log P I selected is problem 5 on the one sheet. So I'm going to grab that now. And we are going to follow. I wrote out the steps. We should be able to follow it pretty easily, I think. Here we are. Okay. I'm pulling it up here. I don't have a ton of room on the sides, but what I'm going to do is in the margins of this, I'm going to follow it through each of the steps and kind of see how we develop our polypeptide chain. So up here, top left, step A. Treatment of Edmonds with Edmonds yields a leucine and a phenylalanine. Edmonds is going to tell us our N terminals. And so this tells us we have 2 chains. So what I'm going to do is put 2 boxes. I meant to leave a little bit more room above. I'll put it in the next one. But LUE or PHE. We don't know how long the boxes are yet. And then off to the side, because it told us we have 2, I'm going to create a little amino acid, not a word bank, but ones we will have to use because it says it contains lysine and aspartate. So we're going to have to use these at some point. We'll leave them in there. We can also put in cysteine times 2 right now if we want, even though we haven't determined it's 2 chains, but we know it's going to end up being 2 chains. Okay, so clue A, this is the information we have. Are we good on that?
Yes.
Okay, next up, clue B. To save space, I'm going to draw it off the main one, but we'll develop after this. So this tells us with clue B that we've got a penta and a tri. So make the top one our penta for space, bottom one our tri. That's where we're at the end of B. Good? Okay. Treatment of the pentapeptide with cyanogen bromide yields a di and a tripeptide. Okay. So cyanogen bromide, this should jump out to you as the C-terminal cleaver for methionine. Now, splitting a 5-peptide chain into a di and a tri gives us 2 spots it can be split. So I'm not going to draw the tri as in the second chain here, just because we're not worried about it right now. But we're going to have a met here or here. This leucine or phenylalanine hasn't gone away, but this is as far as we can take this step because we simply don't know any more information. And now we're going to move to D. Treatment of the pentapeptide with hydrazine yields cysteine. So we're putting cis in here because hydrazine is our C-terminal identifier. LUE, PHE is still up top here, met and met. That's all we can do for clue D. Now to clue E. Also, at this point, if you want, you can cross off one of the cysteine bonds because we only got one left and it's going to be in the other chain. So clue E. Treatment of the pentapeptide with S protease yields a tetra and a mono. So S protease, if you remember what it does, is a C-terminal cleaver for arginine. if we were to cleave here and get a mono and a tetra, that means arginine would have to be in this first box, which is an impossibility. Which means arginine has to be in box number 4, so we can cleave it here. Do we agree with that?
Yes.
Okay, cool. I was just making sure I didn't misspeak. Yeah. So E puts us there. We'll just copy this down. Okay. F, treatment of the pentapeptide with ASP-N protease yields a di and a tripeptide. So F. ASP-N jumps out to me because I really emphasize the N because it means it's an N-terminal cleaver. The only N-terminal we can cleave to get a di and a tri is N-terminal here for this box, which means that we are going to have to put ASP here. And if ASP is put here, that guarantees methionine is there. So we've got all but the first position of the pentapeptide figured out at this step. Does that make sense?
Yep.
Okay. G, treatment of the original tripeptide. So we're talking about this guy here. With endoproteinase, lyse C has no effect. So we've got 3 boxes. The first one is LEU/PHE, a middle box, and a third box. In our bank, we've already burned that ASP. I forgot to cross it off. We've got another cysteine, which has to be in the tripeptide, and we've got a lysine. The endoproteinase lyse C is a C-terminal cleaver for lysine. We know lysine isn't spot 1. We weren't sure if it was spot 2, but we know it has to be in this chain. Since it has no effect and is a C-terminal cleaver, we must assume it is already at the C-terminal for this one. So lysine is going to be put into this last position. Because it's put in the last position, that allows us to guarantee our cysteine bond is there. So we can cross that off and that off. Do we agree G gets us to that spot?
Yes.
Okay. And then treatment of the original tripeptide with chymotrypsin yields a mono and a di. So chymotrypsin is a C-terminal for our aromatics. The only aromatic we know that can be in spot 1 is going to be phenylalanine. And this works on the tri. So this means that phenylalanine is part of the tripeptide with cysteine and lysine, which means that on our penta, we have leucine. So when you are asked to completely redraw the original structure, what we've got is LEU, MET, ASP, ARG, CYS, and then she's kind of a stickler about this. So I strongly recommend not forgetting to put in the disulfide bond, because she will take points off if you're asked to do a amino acid sequencing problem. And she likes it to have a little bit of curve. I probably should have done it like this, but yeah, here. No, there. That's what she would expect as your final answer. Are we good on that?
Yes.
Was that an easy one? I thought it might be medium difficulty. I don't know what you guys thought.
Compared to our exam two, this one was easy.
Okay, that's my bad. If you have another one from the sheet you'd like me to attempt, I can make a video on it, but I don't want to keep consuming the time we have together here to like do another one. So if you want more, let me know and send it to me and I'll do it. But we're going to move on as far as what we're dealing with here. Okay. All right. Next up, let's talk about phase one, phase two metabolism. So I cherry picked from the one sheet that SLA has, the ones that I would bother to learn because I think that they're a lot more useful than the other ones. So I'm just going to go through those quick here. And then I will tell you how I would use them because you're not going to know exactly what structure Dr. Ward will give you, but there are certain things that you can generally expect that she will include just because she has to include something. So first up is, it's number one on the list when you draw them out, but it's the aromatic hydroxylation. So essentially you've got our cyclohexane or phenyl ring, that's better, phenyl ring, attached to everything else. And what you do, you don't have to show the intermediate. I don't believe. What you're going to be installing new, I'll do it in a different color, is an OH at the para position. The likelihood that you have a phenyl ring is very high because you literally need stuff to work with, and this is one that she likes to do. This is generally a likely phase one. Things that make it possible are if there's things off the ring that make it electron withdrawing, specifically halogens, which are usually marked as X. So halogens in the other positions. But this is one I would keep in your back pocket because the chance that you get to use it, astronomically high. Good on that?
Yes.
Yeah.
Okay, cool. Next up, another one that is not guaranteed but often appears is if you have, so very similar to before. I put the circle in. You guys have taken organic. I hope that makes sense. If it doesn't, let me know. But if you've got a methyl group, it doesn't have to be in the para position. I just like to put it in the para position. But this is the benzylic oxidation. And so what we do is we take that carbon here and we hydroxylate it. So this can go through two stages. You don't have to do both if you don't want, but you can either do an OH, or if you were to do both oxidation steps, you'll get a C acid. And this is going to be a phase one likely. So if you see a phenyl ring, you can put something here that is an alcohol, it'll be likely. If there's electron withdrawing groups, it'll be possible. But if there's like a methyl group here, you can oxidize it to this. Good. And this one doesn't have a like possible clause if there's halogens, it just says likely. So that's why I think it's worth knowing. I'm going to move on to the next two. So the likelihood that you guys are given one of these, I simply can't speak to it because I feel like a lot of people put their faith in these two, and then we weren't given a double bond to work with. But this is the alkene epoxidation and or reduction. So with this, you can take it two ways. The first one is simply reducing it by adding hydrogens, which is a phase one possible, which it's really easy. So if you have the opportunity, heck yeah, why not? The second one, which requires the intermediate, is going to be our we stick some OHs on here. And this one is a phase one likely. So if you see a double bond, I think about these two together. It's just you need the double bond to make it work. So if you're given one, that's two easy peasy ones. If you're not given it, these aren't hard to remember. So if you don't get to use them, it's not a huge loss time-wise. But if you do get to use them, they can be worthwhile. And this bottom one can be used as part of a ring. So if you've got like cyclohexane, where there's two here, you can push it through this as part of the ring. It doesn't have to be like a lone double bond. Does that make sense? Actually, I think both of them can be put through a ring. It just looks a little different as part of a ring. And they're still going to be possible for the reduction, likely for the epoxidation. Are there any questions about these two?
No.
Okay. Next up, I am going to put three kind of together. And I think it's going to be beneficial because they are all very similar. So here we've got N, O, and S dealkylation. So with this, we've got a structure, our group of choice. Let's say that overall, these are called Z. So you can put any one of these in here. And then with it, you're going to have, with nitrogen, they will have two. With oxygen and sulfur, there can only be one attachment beyond the R. But what you are going to see is it's going to pick the shortest chain and sever it, leaving a hydrogen in its place. So these chains, I made them different lengths on purpose. So this one has 1, 2 carbons. This has 1, 2, 3. We're going to be severing it here and installing an H. So what you see is R, Z indicative of the nitrogen, the oxygen, or the sulfur. Our nu is going to be an H here. And then we're going to have our original chain maintained. And then it's going to split off. The thing that drifts away is going to be a 2-carbon chain with a double bond O, because the mechanism by which it gets rid of it requires it, and it will end up looking like this. Now, with N dealkylation, O dealkylation, and S dealkylation, there is one caveat. And the caveat is you need a free alpha proton. So there are occasionally structures where you don't have the alpha proton, but if you're pitched something where there is a carbon attached to a nitrogen, an oxygen, or a sulfur, the chances that you can do the dealkylation step is very high. And if you're struggling to find something else, it's not bad to try it in a pinch. Are we good on this? Hello?
Yes.
Okay. Awesome. Let's see. Another one, it's kind of a standalone, is our, I want that, deamination. So this also requires a free, okay, sorry, let me go back real quick. These are all phase 1 likelies. And she generally asks about likelies more than possibles. You're probably likely to see a possible or two, but she generally asks for more likelies, which is why I thought grouping them together and thinking them as ones you want to know was important. Okay, now we can move on. Deanimation. This is going to be a phase 1 likely. Essentially what you're looking for is a R group with a NH2 attached. And with that NH2 on this R group, you are going to need a free alpha proton. That is a requirement. But essentially, what you're going to do is, so in the example they give, they've got a methyl group, a carbon here, an H, and the rest of the structure. So R. Here's our alpha proton. What we see as a result is that NH2 is going to be removed as NH4 plus. The mechanism by which this goes through, we're going to be installing a double bond O. The methyl will still be there, and then the rest of the group remains. So this is the deamination at its most basic form. You need the alpha proton. It's a phase 1 likely. You're going to be releasing ammonia, and you're installing a double bond in the place of this hydrogen and this NH2. Any questions about deamination?
Nope.
Okay. Next up. Dehydrogenation. halogenation. The way we see this is we're going to form phase one likely. Take our group, C, H, Cl, Cl. So you can have multiple halogens participate in this, but you generally won't have to show it more than once. So the result of this is we keep our R and our C. One of the Cl's is going to remain, and in the place of the hydrogen and the chlorine we lose, we're going to be installing a double bond O. That's this at its basis form. You guys good with that?
Yep.
I'm trying to give variety. If this seems tedious, I apologize. I'm just looking at ones that I think are likely to appear based on structure she might give you. And then the last one for phase one is aromatic nitro reduction. So we need an aromatic group. And we've got, what is NO2? It passes a charge around it. I wouldn't worry as much about the charge. Just know that that's a nitro group. This can be made into NH2 and it is a phase one likely. Something that if you remember about this, the reverse of this is a phase one possible, and that is N oxidation, where you put the OHs or the O's back. So if you remember, the forward to making NH2 is likely, the reverse is a possible one. I think it is a worthy inclusion. Good on that one?
Yes.
All right.
Yep.
And last but not least, the one for phase one that I would think is fair. This is desulfuration. Phase one possible. In the chance that you find yourself with a double bond S, you can replace it with oxygen. No questions asked. Desulfuration. That's the last one I want to talk about for phase one. Are there any questions about any of those?
No.
Okay. Seeing none, let's move on to phase two. So for phase two, I picked 3 and only 3. First one is glucuronic acid conjugation. This is phase two likely in all of its iterations. You just have to look for places where you can do it. Stuff that sticks out to me is alcohols and phenols because they're easy to identify. If it's OH, you can do it. If it's OH off of a phenyl ring, you can do it. And she usually includes one of these. If you are struggling to find one of these, your other option is primary or secondary amines. If you were to get a structure without an alcohol phenol a primary or secondary amine, I would say it's simply bad luck, because I think you're going to see these on a structure. But you're going to have to essentially remember you've got an enzyme, UDP, glucuronal transferase, and your coenzyme, which is UDPGA. She does expect the sugar structure, or the UDP, whatever, COOH, H, H, HO, OH, H, H, OH. So in the up position, we'll have an H. In the down position, originally it's OUDP. After it undergoes it, I don't want to draw the whole thing again, so we'll just draw the ring without the specifics. What you change out is this character here, and this is the attachment. So if you're dealing with an alcohol like this, you're going to put an O in there. If you're dealing with an amine, you're going to put an N in there. You can also do this with SH groups. With that, you put an S in there. And then I would use R because you don't want to redraw the rest of your structure. But does that make sense?
Yeah.
Okay, this one, you're guaranteed to be able to use it 99% of the time. So I think it's worth committing. So the next one I would look for is sulfate conjugation. It's going to be a long YouTube video. This is going to be phase 2. Likely is alcohol / phenol. Possible is aromatic nitrogen. So I generally ignore the possible. Additionally, if you had a structure, I'm going to draw over here, R, with an OH. I've seen somebody do glucuronic acid on this one, and then do sulfate conjugation on the exact same one. Rather than looking for a different spot, just do it to the same spot and call them different reactions. And she seemed okay with it. So don't feel like you need to get a unique location for every reaction you do. I've seen people use the same spot and just put it through different reactions, which is why I think alcohol phenols are good places to look for. But what you're going to see, we've got our enzyme, which is sulfotransferase. And our coenzyme is going to be PAPS. In the case of a phenol, this is going to be an O, which is what I would look for. So we've got an RXH, so it's going to be ROH. What this becomes is RX, and then our sulfate conjugation. So double bond O, double bond O, O minus. It can also be N. That's the possible. I wouldn't worry too much about it. Are we good on sulfate conjugation?
Yes.
Okay. And then the last one I would know. And I think this one breaks up pretty easily, is methylation. So phase 2, likely it's going to be alkylamines and alcohols. I would just put alcohols. For possible, you got phenols as the big one. You've also got thiols, less common, and heterocyclic nitrogen. The reason why this one is possible is because it competes with the first one we did, the glucuronic acid. But this one is got good opportunity for both likely and possible. So the alcohols and the phenols are both good. Enzyme we see here is COMT. Coenzyme is SAM, which is where we get our methyl group from. And what we're doing is, so let's draw a phenol quick. So here's a phenol. This would be a possible. If we did it just off of a carbon chain, that would be a regular alcohol. That would be a likely. But what we're doing is we're putting it through the COMT enzyme with SAM as our source. And we're creating a methoxy. So we just add a CH3 there where the H was. This is the possible version down here. Would be a likely version. Are we good on those? Or that, it's one, but it's got two options.
Yeah.
Okay. Good. That is all I wanted to talk about for phase 1, phase 2 metabolism. It may be worth reviewing the enzymes and coenzymes because I know that on the first exam, she literally just had a table and it was like, tell me the enzyme and coenzyme without actually putting it through like any metabolism. She just wanted to see if you knew what was the enzyme, what was the coenzyme. So that is a choice you can make, but it depends on whether or not you want to put the time in. You got to make choices as to what you're going to review. It might be worth 10 minutes of your time, but I wouldn't put a ton of time into it. That kind of wraps up what I want to talk about for phase 1 and phase 2 metabolism. We good there?
Yeah.
Yeah.
Thank you for reviewing that.
Absolutely. So I've got a question. We are at an hour and 45 minutes. Would anyone be opposed if I did the 5 acid base problems in a video and uploaded that tomorrow before our Sunday Zoom? Just because we've been on for quite a while.
No, that's completely fine.
Okay. Aaliyah, are you okay with that?
Yeah, I'm okay with that.
Okay. I'm sorry I said your name. I've been trying not to because it's a video. But yeah, I will do that. I get out of work, I think at 6. So like 6:30, I can work on some of those problems, get them uploaded, and then I can start the Zoom and we can talk about, or I can do them as part of that Zoom tomorrow, if you guys are cool with that.
Whatever you want to do is fine with me.
Okay.
I'm good with whatever.
All right. I will make them part of tomorrow's Zoom, and then anything else that crops up before then, email me. I'll do what I can to prepare for it. I'm going to wrap this up here. Thank you guys for sticking through. And then I will, once it's uploaded, share it for Kate and Alec also. Didn't mean to say their names. Oh my God. Okay. You guys have a good day.
Bye,
Thanks,
Patrick.
Patrick.
Thank you.
Not a problem.